Okay, ECE260 Class 2 in the right place. All right. So I've heard back from the bookstore. They're going to try and order the books and more lab kits. I told them we really need the lab kits by Wednesday, so we'll see what we can do. I did send out an email with all the little bits and bobs that you may need. Everybody get that email? Also in the bottom of that email was the anonymous feedback link and the YouTube link, which has both the lab video where I go through all the wiring and the fritzing and stuff, and also the first lecture. Does everyone have an engineering account at this point? They can log on to the machines in, say, 214. They've got a Z drive. They've got an M drive. Okay. If you have not already looked at the M drive for this course, it's M/ECE260. All right. Let's just for a moment here, as a refresher, numbers. This is a number. Oh, you can't see anything. I'm recording it. All right, numbers. That's a number. What number is that? 100. No, it is not 100. What is it? No, it is not 4. 3. No, it's definitely not 3.
6.
That is an excellent question. What base are we in? Well, I was going to wait around until somebody got around to asking me, and it's base 16. So this number, you were all giving me answers in base 10. And this is a base 16 number. So how does one convert a number that's in a base that isn't our natural base 10 into base 10? What primary mathematical or arithmetic operator do we use to go from another base to base 10? There's a little flow chart. 10 was in the center. What are our mathematical arithmetic operators that we can use?
Division.
Plus, times, minus, divide. Division would be a poor choice, but multiplication would work okay in this case because all of these number systems are positional number systems. This is the 16 to the zeros place, the 16 to the ones place, and the 16 to the twos place. So, taking this, this would be 0 times 1. 0 times 16. 1 times, anybody know what 16 squared is? Naturally 256, yes. 256, which happens to be one of those delightful powers of 2. In fact, 16 is also a power of 2, which is going to lead us right into, I told you yesterday that there was a shortcut. We talked yesterday, base 12, no. Base 10 is kind of where we sit in our heads. But there are other number systems like base 2, base 16, base 8. And we can go from base 10 to base 2 by repeated division. We can go from base 2 to base 10 by multiplication, by powers of 2, 2 to the n. In fact, we can go from any base, let's just add another base out here, n. Oh, that's a terrible choice. Let's do m. M to the n, where n is the place value. So base 8, yep, we can get to base 10 by saying multiply by 8 to the n. We can get from base 16 to base 10 by multiplying by 16 to the n, where n is the place value. Then we go from base 10 to any of these bases. Division by 2, division by 16, division by 8. And, well, division by m, where m is whatever base you want to go to. However, it would be very nice, because we live in a digital world, we're dealing mostly with binary. There are shortcuts that allow you to go from base 2 to base 16 or base 8. Actually, any base x that is a power of 2, there is a shortcut from base 2. So if you are in base 2, you can get to any base without any math, no multiplication, no division. And that's where we're going to start today. So powers of 2, 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. This list of powers of 2 should be tattooed on the inside of your eyeballs by the end of the day. You must remember this list. Because after this power of 2, 1024, we also call this power of 2 1k. So if I start up here with 1k and then ask what the next power of 2 is, that's 2048. But we just call it 2k. 4k, 8k, which is actually 8,192. So we're getting farther and farther away from the actual value, but 8k. 16k. Anybody seeing a pattern develop here? 32k, 64k, 128k, 256k, 512k, and then we get 1024k, which we further simplify as 1 meg, 1 million. If we're describing some unit, bytes, that would be 1 megabyte, 1 megabit, whatever we're describing. 1 million of these things. And again, it's not actually 1 million, 1 followed by 6 zeros. It's 2 to the 20, because this is 2 to the 0. This is 2 to the 10. This is 2 to the 20. And as we continue on in this pattern, we get 1 gig, which is 2 to the 30, and we continue on. Standard SI prefixes K, M, G, tera, exa, no, tera, penta, exa, okay, and so on and so forth. So these powers of 2, mostly I want to deal with these for my number systems. Obviously, a number system with 1 symbol wouldn't be very useful, although you could count in that number system. What would that look like if you counted in base 1? How many symbols would there be in a base 1? It would just be 0. So you'd have 0, and then you run out of digits, so you increment the next digit. 0, 0, 0, 0, 0. So this is 4. So to represent the number 100, how many digits long would that number be? 100. So let's not use that. Let's skip that. But number bases like 2, 8, and 16 are super awesome. 2 is, of course, 2 to the 1. 8 is 2 to the 3. 16 is 2 to the 4. We don't use 4 because, well, it's just kind of too dinky. It's too close to the base 2. And the interesting thing about these bases, how many symbols do we have in base 16? We have 16 symbols. In base 8, we have 8 symbols. And in base 2, we have 2 symbols. If I start writing, remember I wrote all of the first 15 digits. So if I write those digits again, starting at 0, going all the way to 15, and again, I'm going to take that, what's the shortcut in writing out a sequence of binary numbers? Counting out the pattern. So it's, you look at the power of the place, so that's the 1's place, the 2's place, the 4's place, the 8's place, and then you write that many zeros and that many 1's. Repeat as needed. So to get 16 total numbers, I'm going to need 8 zeros, 8 ones, 3. And you know what? We're gonna swap on a grid right here. So that's 0, 1, 1, 1, 1. Nope, that's totally wrong. 0, 0, 0, 0, 1, 1, 1, 1, 1, 1. That's 8 ones. Then 4 zeros, 4 ones. 4 zeros, 4 ones. I need 2 more. Thank you. Well, and this is one of the reasons that I turned on that grid, so that everything would stay aligned, so that I would know when I was making a mistake. One of the biggest problems I see on quizzes or anybody trying to do stuff fast on paper is they don't keep themselves neat. So up here, it's a little messy, but down here, I tried to keep myself to 2 digits per box so that I could always just use those lines as an alignment tool. So then we get 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones. And then the last is every other one changes. Yes, in the back. And your name again was? Your name? Brendan. Okay. This is why we invented erasers. 4 ones. Nope, I went to zeros again. It's amazing that you can say something out loud and something totally different happens. Okay, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Well, that was surprisingly difficult. That was supposed to be the easy part of today. Okay, so that's binary. In decimal, those are just the numbers 0 to 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. But we have other number bases. This is base 10. The number bases we care about are 8 and 16. 16 is the easiest one because most of it is just exactly what base 10 is. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But now things get interesting because we have more symbols. We have to keep going until we run out of symbols. So we have A, B, C, D, E, and F. And I don't think we've ever actually written out base 8, but we're going to do it right now. Okay, base 8 is 0, 1, 2, 3, 4, 5, 6, 7. And that's a total of 8 symbols. So what's the next number going to be for base 8? 1, 0. Not 10, because 10 implies base 10. So 1, 0, base 8. And then we continue on 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. And because 8 is exactly half of 16, we get 2 intervals of 0 through 7. 0 through 7 and 10 through 17. Now, if I look at that repeating pattern, all right, that repeating pattern right there, okay, and I try to find a similar matching pattern in binary. I look for things that are exactly the same across this line. Well, obviously the 8th place is different. It's zeros above that line and ones below that line. What about the 4s column? It's exactly the same. What about the 2s column? What about the 1s column? So in fact, this whole set of 3 bits, it's 3 bits wide here, repeats. So the only difference between 0 through 7 and 10 through 17 is the 4th binary place, right? The first 3 places, the 4's place, the 2's place, the 1's, they're exactly the same. That's because the 1's digit is the same. It's 3 bits because the 8 is a power of 2. So if you have a base that is a power of 2, you can look at a strict number of columns, and directly convert that. Let me give you a larger example here. If I take a new page, which will eventually load, I take a binary number like let's take to color that's working well for me. 1100101, and I wanted to convert this base 2 number into base 8. Rather than going directly to base 10, I can use the property that base 2 and other bases that are powers of 2 are easily transferable by grouping. So I'm going to group groups of 3 because 8 is equal to 2 to the 3. So I take groups of 3. If I wanted to go to 16, 16 is 2 to the 4. So I would grab groups of 4. But we'll try that in a second. And I have to take groups of 3 starting at the right, or at the radix point. Right? There's an implied point there that says anything to the right of this is fractional numbers. We haven't talked about fractional numbers yet. That's our next topic. But we start at the right. So what do I do about this last grouping here? I don't have 3 digits. Yeah, add 2 zeros. The same rules that we learned in grade school apply to all number bases. You can add zeros to the left of a number and not change it. And you can add zeros to the right of a decimal point and not change anything. All right, so now I've got 3 groups, and all I have to do now is convert these 3 binary digits into an octal, or a base 8 digit. And if you don't know what this is, you go back and you look at your table. What is 101 in base 8? Well, actually, in most of the bases, it's 5. What is 100? Well, that's 1 less than 5. That's 4. What's 001? 1. That one's easy. So the answer to this question is 145, base 8. This is why it's so important to get those first 16 numbers tattooed on the inside of your eyeballs, because if you can just look at a binary number and say that 1100 is either a 14 base 8, think about it for a second, am I right? 14. Or in base 16, it's a C. Let's just check that. Let's go back, look at the table for a moment. 1100, what is it in hex? It's a C right there. Okay, you have to memorize this stuff. I have been shown some pretty compelling evidence that says I need to give you guys skills tests more often. So expect speed tests on doing this kind of stuff. 30 questions, 2 minutes. You got to be able to boop, 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 boop. Okay. So if I were to, now you guys try grouping this in groups of 4. Again, the original number was 1100101. Tell me what this is in base 16. Again, you just have to group it in groups of 4. "30 questions, 2 minutes. That's what, 4 seconds per question? Maybe that's a little unreasonable, but not by much. Or maybe I give it to you and you have until I finish. No, that sounds terrible. That's not fair. You shouldn't do that. All right, who's got an answer for me? You should be done. All right, well, if you're going to raise your hand, I'm not going to call on you. Someone who looks uncomfortable. You there, playing with your ear. What's your name? Matt, what did you come up with? 65. Well, let's see if I agree with that. You grab a group of 4 here, a group of 4 here. You fill in a 0. Yeah, I think that looks like a 6 and a 5. So that's 65 or 65 base 16, 65 hex. Always, just like in most other applied sciences, you got to put a unit on it. All right. So 65. That's all well and dandy. So now Let's go back to that little state diagram here. So now there's a really quick way to get from any base that is 2 to the x to base 2. What about going from base 2 to base 2 to the x? What about from base 2 to the x, or base 16 back to 2? Right, we got to cover these situations. Well, in this case, if I give you the number 1, 2, 3 base 16, very creative number I've just made up here, how would we convert this to base 2? Well, you just take each digit, 1, 2, and 3, and you assume that there are 4 places associated with it. And you fill them in. 1 in binary, 0, 0, 0, 1. 2 is 1, 0, and you just fill in the rest with zeros. 3 is 1, 1. That's it. Your turn. What is C260? Yeah, C26. We'll call it there. C26 in base 2. You finished? I'm seeing actually a lot of nodding heads. This is great news. Who wants to volunteer? No volunteers? Yes, your name. Sakina. What did you get?
I got 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1.
Yes. And it's perfectly reasonable to write your answer as I've done on the board here. Very fixed width. But I tend to make reading easier, specifically because of this shortcut, I tend to group things in groups of 4. So 1, 1, 0, 0, a little bit of a space. 0, 0, 1, 0, 0, 1, 1, 0. That way it's very easy if you're trying to transcribe this number somewhere else or read it to somebody else, or you're just showing it to somebody. Because I don't know about you, I can't memorize 12 numbers worth a darn. I can still remember my home phone number from when I was 6 years old, but a binary number like this, not a good chance. So if I'm going to transfer this, and you'll see me do this throughout the semester, if I've got a binary number up on the screen and I'm going to transfer it to the next page, I will quickly convert it to hex in my head, because I can remember 3 hex digits. That's easy for me. Might not be for some people, but for me, that's the way that works for me. So I recommend grouping by 4. Okay. Grouping by 4 has another benefit. Most of what we do in follow-on courses is based around 8 bits. 8 bits is 2 4-bit quantities. By the way, 4 bits is called a nibble. 8 bits is called a byte, which for a really long time I just kind of took on faith and went with it. And one day I realized that a nibble is a really tiny byte. It's not quite a full byte. And I laughed for days that I'd never realized. Okay, so that's all well and good. All right, so we know how to go from 2 to 16. We know how to go from 16 to 2. We know how to go from 10 to anything. We need to go anything to 10. So you should easily be able to take this number here, 15.25, and tell me what that is in base 2, right? You can do it? Yeah. Let's say that it's base 10. Yeah. Well, there's one added wrinkle. Tiniest speck has changed this whole problem. If I asked you to take 1525 base 10, I think with a little bit of time, you could give that to me in base 2. So a longer number would take a couple of divisions to deal with. But the addition of a decimal point. Changes everything. So before we tackle this, let's just pause for a moment. 0.25. How do we deal with this? Well, before we deal with the decimal number, we are going to binary. What do the binary places look like? We know that we have digits to the left of the binary point. It's a binary point, not a decimal point, because we're not in the decimal number system. But this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so forth. What about on the right side? What is this the place value of? 2 to the negative 1. And that matches up with our decimal number system because this is 10 to the negative 1, 10 to the negative 2. So we can continue on 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, and so on and so forth. Now, what is 2 to the negative 1? Well, that's 1 over 2 to the 1, which is 1/2, which is 0.5. 2 to the negative 2 is, well, we can deal with this, 1 over 4, which is 0.25. 2 to the negative 3, 1 over 9? 8? 1 over 8, which is 0.125. It's half of 25. Half of 25 is 12.5, so 0.125. Half of 12.5 is 0.625. All right. I begin to lose it at this point in terms of being able to do it in my head, but the process is the same. All right, so we're going to cover base 10 to base 2 decimal numbers first because it's easier mathematically. All you're going to do is you're going to take 0.25, whatever the decimal number is, and you're going to multiply it by the base you want to end up in. So in this case, we want to end up in base 2. What is 0.25 times 2? It's 0.5. 0.5. I'm then going to take this number and bring it down and multiply it again. 0.5 times 2 equals 1.0. And this is the trick. Every time I bring a number down, I'm going to ignore the integer portion of it. So I'm going to strike the integer part of that and bring it over 0.0. Once I find something on the left that is 0, I'm done. And I read from the top down, so I end up with a 0 and a 1, only looking at the integer parts. That wasn't the best example to showcase all the interesting things can happen. Let's take a larger example. and I'm going to cheat, 6875. 0.6875. If you want to follow along with me, oh, interest. Oh, there it is. 0.6875. So to deal with this, I start by multiplying it by 2. What is 0.6875 times 2? It's 1.375. So what I'm going to multiply next is not 1.375, but 0.375 times 2 is 0.75. Okay, then I take 0.75 times 2, that's 1.5, right? Sometimes I make leaps like that, and I make a wrong leap. It's like 2 to the 3 being 9. 1.5, so then I take the integer portion off. It's 0.5 times 2. That's equal to 1.0. And then I've got 0.0, so I'm done. I stop there. And then I read from the top down and write it out. 1, 0, 1, 1. So this number in base 2 is 0.1011. It's pretty cool. There is one thing that can go wrong here. Okay? One thing that can go wrong. I'm going to need a whole nother page. Can I go to the next page on this? Okay. Let's take a nice simple number. Nice clean round number. 0.65. I want to know what that is in binary. So what do? I think at this point we kind of see the process here. Times 2 equals, yep, 1.3. So then we take 0.3, we multiply it by 2. What's 0.3 times 2? That's 0.6. 0.6 times 2 is 1.2. So then that's 0.2 times 2 is 0.4. 0.4 times 2 is 0.8. 0.8 times 2 is 1.6. 0.6 times 2. Wait, didn't I already do 0.6 times 2? What does that mean? What does that mean for me as the calculator of this quantity? Yeah, it keeps going. So much like what is the decimal representation of 1.3? Oh, sorry, 1 divided by 3. 0.3 repeating. It never ends, right? What's the mathematical term for a number that doesn't end? So this binary number is going to be equal to, and again, we're reading from the top down, 1, 0, 1, 0, 0, 1, with, I think, that much repeating, I believe. Yeah, that looks about right. Because that's where I start duplicating this. So there are some that you can compute until the end of time. And if you don't have enough smarts to recognize that it's going to happen, you will waste a lot of time trying to convert a number that will never stop. I was listening to an audiobook last night, and something started going wrong with it. It started skipping, popping, doing weird stuff. But it was playing fine on my computer in various parts. So I opened it up to sort of look at the raw waveform. And so it started decompressing it from a compressed file to a raw file. And it was a fairly large audiobook, and it was going along. So a couple minutes in, it was counting down. Okay, 5 seconds left, 4 seconds left. It was 98, 99% complete, 100% complete, 0 seconds left. 1 second remaining, 101% complete. It started counting up. It got to like 230% done, and then I was kind of like, all right, maybe there is a problem with this file. But that's the kind of error that this can cause. I don't know what the actual error is. I just re-downloaded it from Audible, but anyway, so just be aware that sometimes this can be a problem. You should keep track of what your numbers are, because all of these are so tiny, right? 1 decimal place, and it is a decimal place, not a binary place. 1 decimal place. It's so easy to multiply these, and yet we get a number that goes on forever. All right, putting this all together, 15.25. We actually can't do it all in one step, though, because in order to convert 0.25, we have to have 0.25. So what we do is we split it up. We split up to the left of the decimal point and to the right of the decimal point. We do 2 conversions. So 15 in binary, I'll give you a hint, is 1111. 25 we've already done. That's 0.01. So when you put it all together, it's 1111.01. You don't keep that 0 as part of your number. Okay, you add them. So you take 1111 plus 0.01, and you end up with 111.01. All right. Like that. Conversion between bases. Yeah, we're looking good. All right. We've got about 20 minutes. This is going to be good. Do I talk about math first? Or I've got to talk about math. Everybody likes math, right? You're all engineers. Math is good. Math doesn't get more basic than 2-digit arithmetic, except what? There is an F there. So what? Yeah, this is all math in base 16. So this is actually not as big a deal as it sounds. You take F. This stuff you can kind of count on your fingers. F. What comes after F in hex? 1, 0. That's adding 1. So 1, 1, 1, 2. So it's a 1, 2. So it's the same thing. You take the least significant place, you put that there. You carry the 1 to the 16's place. So this is 16 1s plus 3 16s is what? That's 3 plus 1 plus 2 is 6. That's it. 62 base 16. Do we have time? We may have time for a Tom Lehrer song. I don't know how that works if I'm posting the video to YouTube, though. It's going to be a copyright thing. I may have to stop before we get there. I don't know if I'm monetized. That's, well, best to err on the side of caution when it comes to copyright infringement and plagiarism, especially at an academic institution. For education purposes, right? I mean, I get paid to do this, so maybe not. Go ahead, do me some mirth there. This is base 2. What will this be? As an answer. All right, going through this now. Let's see. 1 minus 0 is 1. 0 minus 1 we can't do. So we take 1 from the 4's place, make it 0 4's, regroup. You change that to 1 0 in the 2's place. That's 2 minus 1 is 1. 0 minus 0, that one's a tough one. 0. 1 minus 0 is 1. And we could have cheated. We could have looked at this and said, hey, this is 13 minus 2 is 11. And this is 8 plus 2 is 10 plus 1 is 11. Yep, we're still good. All right. Easy so far, right? It's just math. It's the same thing we've been doing a long time. Well, computers can't actually do subtraction. It's a little weird. They don't know how to subtract. They can add just fine, but they can't subtract for the following reason. What is this number? We have established as a negative number because this is definitely larger than this number, right? So, but we go through the same process, right? 0 minus 0 is 0. 0 minus 1, you can't do it, so you take a 0 here, you put a 1 0 here, that's a 1. This is a 0 minus 1, so you have to borrow from this digit, and then you borrow from nothing. So we need another way of dealing with subtraction, which leads us to the vocab words that you will all come to hate. Ones complement, and twos complement. Okay, these are a process by which we can do subtraction without actually having to subtract things. First, big star here only works with numbers of fixed length. Fixed length in bits. I'll put it in there, in bits. So every number that you're going to use in this mathematical operation must use the same number of bits. So it would be wrong to try and do this with some number like 1100 and then 10. That would not work. It is important that they all have the same number of bits. And you can do that by zero filling. Okay? But it only works with the same number of bits. So if I give you two numbers that are different sizes, first thing is make them fixed bits. So let's define one's complement for a second. It's dead simple to find the ones complement of a number. If you have a number, any number, there it is, pick the number at random. To find the ones complement of the number, every 0 becomes a 1. Every 1 becomes a 0. That's it. You complement each number, meaning you invert each digit. So 11010110 becomes 001010001. It's inverted. And that's all there is to one's complement. Two's complement is equal to the ones complement plus 1. To get from the ones complement to two's complement, you add 1. So if we were doing the same procedure here, use the same number, 11010110. That's our original number. Then our ones complement would be 001010001. And finally, our twos complement would be the result after we add 1 to it. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, at which point everything else is the same. And that gives you the twos complement of your number. So the twos complement of 11010110 is as follows: 0010110. Well, what good does this do us? Now we have this procedure for finding twos complement numbers. Go ahead, find me the twos complement of that number. What did you get?
1010.
Yep, looks right to me. So you do the 1's complement of that, 1, 0, 0, 1. You add 1 to it, that's 1, 0, 1, 0. Now, hang on a second. These are just binary numbers, right? What is this number in base 10? 0, 1, 1, 0. 6. What is this number in base 10? The 1, 0, 1, 0. It's 10. Which is actually a very convenient mnemonic, by the way. 10, 10 is 10. 10 is 10 is 10. So what the heck does this, why would we ever need this 2's complement? Well, because this is a 2's complement representation of a number. It actually represents -6 in what we call signed numbers. So as unsigned numbers, it's 6 and 10. As signed numbers, this is 6 and -6. So the signed domain, this is a signed 2's complement number actually. Signed 2's complement has the ability to represent both positive and negative numbers using only binary symbols. When we wanted to do something in math, we used 0 through 9, and then we also had a positive and a negative sign. Well, computers don't have a negative sign thingy. They have to use one of their bits. And here's the interesting thing about signed numbers. If you are using signed numbers, the most significant bit, or MSB, which is the one all the way to the left, is an indicator of sign. It's the sign bit. 1 means negative, 0 means positive. Now, if you have a positive number, how do I do this? Pause. Positive number. The lower bits are the magnitude. The magnitude of that sign number. So I look at this number. The upper bit is the sign bit. It's a 0, meaning a positive. The lower 3 bits there are the magnitude. So you just look at them as a binary number. What is 1, 1, 0? It's still 6. If it's a negative, the lower bits, and I should say the 2's complement of the lower bits. So if the 2's complement is a function, if you put those lower bits into the 2's complement function, you will find the magnitude. Okay, so I take those bits, invert them, 1, 0, 1, add 1. And actually, I said everything has to happen in the same number of digits, so it's all 4 digits, so you even invert the sign bit. But you leave it like this, so that's inverted, then add 1 to it, 0, 1, 1, 0. That is a 6. That's your magnitude. So we have 2 ways of finding the magnitude of a number, whether it's positive or negative. If the number is a positive, you just look at the bits and convert them as if they were a regular binary number. If it's a negative number, you have to first take the 2's complement. So you're actually undoing the 2's complement of what you just did. And then that gives you the magnitude. Okay. Here's the really interesting thing. We've got time for just this quick example. 6 minus 2 should definitely be 4, correct? 6 as a 4-bit quantity is 0, 1, 1, 0. Negative 2, well, 2 is 0, 0, 1, 0. The 1's complement of that is as so, and the 2's complement would therefore be that. If I want to subtract 2 numbers, remember, 6 minus 2 is the same as 6 plus negative 2. And that's how we're going to do this. We're going to add 6 plus negative 2. So this is negative 2. So 1, 1, 1, 0. Now we do some addition. 0. 1 plus 1 is 0. Carry the 1. 1 plus 1 plus 1 is 3, which is 1, 1. So that's a 1, carry a 1. 1 plus 0 plus 1 is 0. Carry the 1. And here's the most important thing. Remember, big star at the start of this. Everything must be in the same number of bits, including your answer. So if you have something that goes beyond 4 bits, it's gone. You ignore it. So what is this number? First off, look at the sign bit. Is it a positive or a negative number? Positive. So you look at the lower bits. What is the magnitude of this number? Is that correct? I will see you on Monday. Oh, let's stop the recording.